3, 2, 1, let's go. Notes for 3-3. Okay. I'm going to be coughing my way through these ones as well. Alright, so last time we introduced matrix multiplication, and the goal for today is to talk a little bit more about matrix multiplication, and then we will look at the specific case of not multiplying two matrices, but rather a matrix multiplying a vector. So we'll unpack that. Alright, so let's recall that if I have matrices A and B, where A is an m by p and B is a p by n, note the number of columns of A and the number of rows of B need to match. Their product is then defined to be the m by n matrix. So note the rows of A and the columns of B become the rows and columns of A and B respectively, the sizing. It's the matrix A times B, whose jkth entry is given as follows. And as we noted, this is simply the dot product of the jth row of A with the kth column of B. All right. Okay, so we introduced that this is the proper way of multiplying matrices. We motivated it as the proper by going, well, the proper way of multiplying vectors was the dot product, so the proper way for matrices should be built off of that. And we'll unpack today the real power behind the definition of matrix multiplication, why it's defined this way, in context of linear systems, and yeah. All right, before we do that, let's go ahead and investigate how matrix multiplication interacts with transposing. So we've already seen matrix multiplication interacting with our matrix operations of scaling and adding matrices pretty well, that scalars can move in and out of the product the way you would want it to, and addition and multiplication of matrices distributes, so that's good. All right, and it turns out that transposing and multiplication works out pretty well. We get this neat little formula saying that the transpose of a product is the product of the transposes, but in reverse order. Now, note that clearly it had to have been in reverse order before we even got into this, because B transpose is a P by N, and A transpose is an N by P, so the only way for that multiplication to make sense is if it was B transpose times A transpose, even though A times B is the appropriate order here. So we don't get our usual favorite phrase in math, the x of the y is the y of the x. We instead get the x of the y is the y of the x, but in reverse order. So for the deep lore enthusiasts, some people would refer to transposing then as a not multiplicative operation, but a anti-multiplicative operation, because it swaps the order of the product. All right. Anyway, let's actually quickly see the details of the proof of this one. This one's pretty straightforward. Again, a lot of these proofs right now are a lot of index management as we're sort of building up the various equations that hold before we can start manipulating those. And again, if I'm proving two matrices are equal, I just want to show that their jkth entries are equal. So you start with the jkth entry of AB transpose. The transposing swaps the order, write out the multiplication. Okay. Note that I've got the k and the j kind of in the wrong spot, so I want to flip them, and I can get the k to the right and the j to the left by noting that, well, that's the transpose. And then here's the slick move. Note that at this point this is a product of two real numbers, and real numbers are commutative, so you can swap the order then, and then now we see the j and the k are in the right spot for matrix multiplication. Cool. Neat little thing. So that's why the order kind of swaps, because like at this point, right, you got to use the commutativity of the multiplication of real numbers. Neat little thing happens there. All right, as a consequence, our complex version of transposing, adjoining, will also have the same property that the adjoint of the product is the product of the adjoints in reverse order, and this little fact might be useful for the exam review. All right, cool. All right. Now that we've got that taken care of, let's go ahead and set our sights on the big thing for today, which is multiplying matrices by vectors. Okay. Now, any element of Rn is really an n by 1 matrix, so I can multiply it then by matrices. And note that if I do A times X then with this viewpoint, I'll get an m by 1, which then I can just view as an element of Rm, is what that should say. Let me quick change that. Yep. Hey, there you go. Anytime, oh, there it is, fix it. All right, so given a matrix M by N and an element of Rn, I can define their product Ax, which lives in Rm, as follows. All right, so note the Jth entry of this is right the usual matrix multiplication, right, where we're taking the Jth row of A and just dotting it with the vector x. Okay. Cool. There you go. So that's the definition of matrix times vector. And while we're here, in the previous video, I jumped the gun and tried to prove this result. So let's go ahead and just actually do this now. And so note here, this tells us that the inner product of AZ with W is the same thing as the inner product of Z with A star W, meaning that I can kind of move my matrix over to the other component of the inner product as long as it's the adjoint of the matrix. And like I said, when I first was trying to prove this, before I forgot I didn't define matrix multiplication yet, this ends up being like one of the most powerful things like ever. The things you can get away with this is pretty astonishing. And in particular, there's going to be a eigenvalue result that we're going to need, and it immediately pops out of this formula. So, all right, and the proof of this one is pretty lengthy, as you can see here, and I'll not go through all of the details of it. I will just point out that this is like the ultimate unravel the definition problem, where write out what this is, well, it's this. Okay, well, write out what this is, it's this. Now, at this point, the step you pull is that this complex number gets pulled into the summation, which it's allowed to, right? Multiplication distributes over sums. And then in here, you do a little swapperoo of the summations, which you're allowed to do because addition is commutative. It doesn't matter the order in which you add things. Okay, now in this summation, it only depends on k, but this term only cares about z, so you can pull it out. And then now you just re-ravel this back into precisely what we want it to be, the AZW conjugate, and there you go. Okay. So note the use of the conjugate of the conjugate, and yeah, that's right. Again, a lot of details here, but it's just unraveling definitions at each single step. So I'm gonna kind of breeze through it there pretty quickly, but I hit the big bullet points. All right, cool. All right, so like I said, we're gonna use that in one very specific spot for eigenvalues. It's gonna be very cool when we do it. All right, now let's get to the big thing for today. All right, so let's recall that if I give you a system of linear equations, there it is, beautiful, we can break this down into three pieces, right? The matrix consisting of the coefficients A, the vector x consisting of the unknowns that we're trying to solve for, and the vector b consisting of the right-hand sides. Well, if you look at each one of these, well, hey, wait a minute. Each line here looks like a matrix times a vector, equaling this right-hand side. So indeed, this system of linear equations is really ax equals b, where the ax and b are all the usual terms, right? Just look at the jth entry of a times x as defined, and you'll get precisely what's on the left-hand side. Beautiful. So we now have that every system of linear equations is really a matrix multiplication in disguise, which wasn't too shocking because, as we noted when we introduced dot products, a system of linear equations looked a lot like dot products, but now we have it very precisely written out. And now, with this breakdown, where any system of linear equations looks like an ax equals b, this seems to point to a new solution method for us. I should be able to sort of multiply this by something to isolate x. Right, we know that you can't necessarily divide by a matrix. That doesn't make any sense. But if I were able to multiply a by something that would remove it from the equation, then I'd be able to isolate x. But note that if I were to do that, I would need matrix multiplication to be associative, right? Because if I multiply this by something, I'd probably want to move parentheses around to isolate x. And as we noted last time, sort of our parting shot, all of our usual multiplication facts, so identities, distributivity, commutivity, we discussed all of those, but we didn't get the last tivity, which was associativity, which we will now prove And it's going to be a sequence of propositions that will also establish some other important facts about how matrix multiplication behaves. Okay, first up. Multiplying a matrix by a standard basis element isolates the column of your matrix. So if you want to get the kth column of your matrix and you want to get it as a matrix multiplication, you multiply by the standard unit vector ek. Right, and that's pretty easy to see because, well, look at the multiplication itself. The jth entry of this would be this expression right here, but the standard unit vectors are 0 when the indices are different and 1 when they are the same. So the only thing that pops out of this is the jkth term, which is the jth entry of the kth column. Hey, there you go. Cool. Pretty straightforward proof. Now, another neat fact here now, because we know the kth, multiplying by the kth unit standard unit vector will give us the kth columns, this now reveals a neat little thing. If I know I've got two matrices such that A times the standard unit vector is always equal to B times the standard unit vector, then it's got to be that A and B are the same matrix. So note here, we kind of get a cancellation. We noted that you can't in general get cancellation of matrix multiplication, but here we see that if you have equality with matrix multiplication and enough equalities, not just one equality, you can actually get away with canceling the EKs and getting A equals B. Right, and again, this is pretty straightforward because we know that multiplying by the standard unit vector just gives you the kth column, and this is saying that all the kth columns are equal, which would mean that all the entries are the same, which is what's written out right there. Okay, oh, pretty cool. All right, what's next on our list as we're marching towards matrix associativity? Okay, next up, another way of looking at A times X. So note that we can view this as the jth rows of A dotted with X, but it turns out you can also view it in terms of the columns of A. It is the linear combo of the columns where you're scaling by the entries of X. And this pops out because X is equal to a summation involving the standard unit vectors, as we noted. You can pull it apart like that, and then simply multiplying this equation by A, then since matrix multiplication distributes and pulls out scalars, we simply get that. And as we just proved, multiplying by the standard unit vectors gives you the columns of A. So this gives us a column way of looking at A times X. It's the linear combination of the columns. We can also view it as a row, right, where the rows of A are dot producting with the vector X. But now we kind of see there's another way of doing it as well. Pretty cool. Oh my god. All right, what's next on the list? All right, next up, this result, which says that if you look at the kth column of a product, it's the same thing as multiplying the matrix on the left by the kth column of B. So note, here we have the matrix multiplication, here we have matrix times vector, and this is revealing that the kth column of a matrix multiplication is really a matrix times a specific vector. Yeah. Okay, and I'm claiming two vectors are equal, so I need to show that if I look at the jth entry, they are equal. So look at the jth entry of this, that's the jkth entry of the product, which is this. This right here is the h entry of that vector, and hey, matrix times vector, there you go. All right, so ultimate unraveling of the definitions proofs going on here. All right. All right, well, we're almost there. So next up, we're going to prove that you have associativity of matrix multiplication as long as the third thing is a vector. So here we see that if you were to do A times this vector, that's the same thing as doing A times B times that vector. All right, and the secret sauce here for that is to, well, I know that matrix times vector is the linear combination of the columns, the A distributes, and then I have matrix times column vectors, which are just the column vectors of the matrix multiplication, and then you've got a linear combination of the columns of the matrix multiplication, giving me the matrix multiplication times the vector. And equipped with that, we are then home free to prove that finally matrix multiplication is associative, indeed. We got it. It's time to prove the thing. All right. And this is the ultimate just move parentheses around proof. So note, if you wanted to prove two matrices are equal, you need to show that their JK entries are equal, or, as we just learned right up here, show that multiplying them by these standard basis elements always lines up. And that'll be the method of attack for this proof. So you look at EK times this. All right, well, following the previous point, I've got a matrix times that vector. So this says that it's really the leftmost matrix times the vector, which in this case would give me that. So I can move the parentheses over like this. And then we apply the same logic. I'm allowed to move these parentheses over to here. Okay, and then apply the same logic again, where I've got matrix times vector. I'm allowed to move those parentheses over like that. And then again, I'm allowed to move these parentheses over like this. And indeed, these then line up with each other when you multiply by the standard unit vector EK, which would guarantee that those two matrices are equal. And ta-da, we've done it. Matrix multiplication is indeed associative. And that concludes the proof. All right, and our goal for next time will be to then finally address the question of inverses of matrices, and we'll see that we've kind of already laid an incredible amount of groundwork to quickly rattle off some facts about that. So that'll be what we do in person tomorrow. I'll see you then.